Today, I will be talking about capacitors and RC circuits. RC circuits stands for circuits that have resistors and capacitors in series, parallel, or in both configurations. Capacitors, on the other hand, stores and releases electric energy in the form of an electric field in a short time. A capacitor is made with two metal plates with a non-metallic and non-conductive material between those plates. Most capacitors that you will see are in black and white. The two metal plates that you see is pretty much these two leads right here. And for this capacitor design, the two metal plates, along with the non-conductive and non-metallic material, is wrapped around in a cylindrical configuration. For most types of capacitors, they are polarized, meaning they have a positive side and a negative side. You can tell which side is negative and which side is positive by two things. One of the things is that the negative side is marked on the capacitor. So as you can see right here, meaning this side here is my positive side. And another way to tell is that the length of my positive lead is longer than my negative lead. So this here, the longer lead here is my positive lead, and the shorter lead here is my negative lead. This is important because of the electric field that holds and releases the electric energy in our capacitor. And we have electric field lines that go from the positive plate to the negative plate. The electric energy that is stored in our electric field by our two metal plates creates a potential difference or a voltage that the capacitor would hold and release. And you can think of this process as the following equation, where the strength of the electric field, which is denoted as E, is equal to the voltage of our capacitor divided by the distance of our two metal plates. And our strength of the electric field essentially determines how dense or how compact or electric energy is in our capacitor. To better define what the electric field is, the electric field is the force of electric charges. And this force is either the push or pull of charges in the environment. You will also see that the positive charges are being pushed and the negative charges are being pulled. And this is just defined by the electric field lines that is created that would go from the positive plate to the negative plate. And the electric field lines that go from the positive plate to the negative plate is parallel, and also they do not cross each other. And the electric field lines define our electric field. And I'm gonna go ahead and draw a diagram of what this looks like. So here's my diagram where this is our positive plate, this is our negative plate, and where these are the electric field lines. And between our positive plate and our negative plate, we also have our non-metallic and non-conductive material that is between those plates. And as I'll shade in here, we have our non-conductive and non-metallic material. And you can also think of this non-metallic and non-conductive material as the dielectric material. And when you're drawing the electric field lines like this, typically if you have a stronger electric field, you would have more and denser lines. And I'll draw another diagram to demonstrate a stronger electric field. And as you can see here, I have more electric field lines, and also they're more dense or more packed together. And this is just in comparison to the above diagram that I have here. We can think of the electric energy that is stored inside our electric field here as the capacitance. And capacitance is just what our capacitor is measured at. And our capacitance is measured in farads, which is denoted as F. And usually you will see capacitance measured in microfarads. And the construction of a capacitor determines what our capacitance is. And we can write the following equation to determine what our capacitance is based on the construction of our capacitor. And this is our equation here. Capacitance is equal to K E naught times A over D. I have K, which is the dielectric constant of the material between our two metal plates. And you can look up different dielectric constants of different materials that you can use inside the capacitor. You have E naught, which is just a constant defined as the permittivity of free space. Then we have A, which is our plate area. Generally, you'll want to keep your plate areas the same. If one metal plate has a bigger area than the other plate, the smaller area plate will be considered. Also, for the area of the smaller metal plate, it has the risk of having a spike in voltage during the discharge of the capacitor. Finally, we have D, which is just the distance between our two metal plates. For the capacitor, if you're making a circuit schematic diagram, has the following symbol. And this is our symbol here. The symbol with the straight line is typically your positive side, and your rounded curved line would be your negative side. And for cases where your capacitor does not have a polarity, or it does not matter which side is positive or which side is negative, your symbol would look like this, where either side could be positive or negative. This also means that the electric field lines can go in either direction. This is possible because the dielectric material that is selected would allow the buildup of charges to go in either direction. So as I'll write down, non-polarized capacitors are usually used when you're working with alternating current. And there are generally three different types of capacitors that you can pick from. You have your electrolytic capacitor here, you have your film capacitor here, which is shaped like a square, and you have your ceramic type capacitor, which generally has a yellow color and has a rounded shape. And your capacitors could be polar or non-polar. Ceramic and film capacitors are generally non-polar. Electrolytic capacitors are generally R-polar, but they can also be made into non-polar capacitors, like this one I have here. Let's now talk about how a capacitor charges and discharges. A capacitor will charge itself when an external voltage source provides charges to the positive plate of your capacitor. And the capacitor will stop charging once that voltage source is removed. Once the capacitor is fully charged, the electric energy would be stored in the electric field. And that electric energy is stored inside the electric field unless one of the two things happen. The first thing is when the capacitor stops charging and experiences a leakage of current. And this leakage of current is caused by some flaws that could exist in your dielectric material. The second thing is that a path exists that connects the capacitor's positive and negative leads together. And that's also given that the capacitor is not charged by an external voltage source. And the time that the capacitor would take to fully charge and discharge is given by the following discharge equation. And here I have my discharge equation, and I've defined the variables in the equation as the following. Vt is the resulting voltage after time t. E is a constant, which is Euler's number at 2.718. T is the time measured in seconds. R is the resistance measured in ohms. And C is the capacitance measured in farads. And this term, e to the negative t over RC, determines the percentage of charge or voltage that is left in your capacitor. Initially, your fully charged voltage is V0, and over a short period of time, your voltage is going to decrease by discharging your capacitor. This here is my summary of what e to the negative t over RC represents. And if you want to find the discharge percentage, you can just use 1 minus e to the negative t over RC. And if you want to find your charge percentage based on time t, You can also use 1 minus e to the negative t over RC. So let's say T in our voltage discharge equation is equal to R times C. Our result for this term is e to the negative 1. And e to the negative 1, if you put it into your calculator, it's going to be 0.3678. And that represents 36.78% of the charge or voltage that is left in your capacitor. And if we want to find the discharge percentage when discharging our capacitor, or the charging percentage when the capacitor is being charged, we can use 1 minus e to the negative t over RC. And substituting negative t over RC for 1, we would get 63.21% as our result. And if we want to find out when our capacitor would be fully charged or discharged, we would just have to make sure e to the negative t over RC is equal to 1, or at least close to 1. And we can do that by substituting t to 5 times RC. And our result for e to the negative t over RC, we could simplify that to e to the negative 5. And for the result of our voltage discharge equation, we can simplify it, and e to the negative 5, if you put it in your calculator, would equal to 0.0067, or in other words, 67%. Or in other words, we have 67%. And basically, you have this much charge left in your capacitor after 5 times R times C seconds have passed. And if you want to find the discharged percentage or the charging percentage after time t, you would just use 1 minus e to the negative 5. And I do keep mentioning electric energy that is inside your electric field. And the electric energy is just proportional to your capacitance. Another thing that I want to clear up is that capacitors would work differently when you're comparing their usage for AC versus DC. When you're placing a capacitor in a DC circuit, the resistance for your capacitor is infinite, or it's an open circuit. This is because the two metal plates that you have in your capacitor don't touch each other, thus making it an open circuit. But if your capacitor is used in an AC circuit, your capacitor now has a resistance called impedance. And to write this down for a better understanding, the impedance of your capacitor is denoted as the subscript of C. And you can use this following equation to find the impedance of the capacitor. If you're using your capacitor in a DC circuit, F, which represents your frequency, is going to be equal to 0, and thus your resistance or your impedance would be infinity. And to write the definitions of our variables down, and this is just 2 pi right here, if you were wondering. And one final note that I would like to make is that when you're using a capacitor in a DC circuit, keep in mind that the 2 plates of your capacitor doesn't connect, thus making your resistance infinite. And what that means is that when your capacitor is charging, say my right hand is my positive plate, and say my left hand is my negative plate, when my positive charges build up, my negative charges go out the other way. And this would go on until my capacitor stops charging, or when it's fully charged. And when the capacitor is fully charged, the capacitor acts like an open circuit, which means that no DC current or electricity can go through the capacitor. So this here is the summary of what I said. The current that is going through the capacitor can be written as the following equation. I have I, that is denoted as the current that is going through my capacitor, C is the capacitance, and dV over dt is the change of voltage over time. And one thing to note is as dV over dt has a higher and higher value, or as the capacitor experiences more extreme changes, one thing to be careful about is that the capacitor will most likely overheat, and the energy or the voltage stored in the capacitor will be much less. And with this in mind, let's go ahead and talk about the voltage limitations that you will see on your capacitor. So going back to my capacitor here, you can see that the capacitance is 1000 microfarads. You can also see that the voltage limit for this capacitor is 16 volts. And if you exceed the rating of 16 volts, the capacitor will overheat, the dielectric material will break down, and the capacitor might even explode. And I'm going to go ahead and demonstrate what I've talked about before. If dV over dt gets too large, the effectiveness of the capacitor would decrease. So let's now talk about capacitors in parallel versus capacitors in series. The total capacitance, if you have your capacitors in a parallel configuration, is the following equation. And the total capacitance when your capacitors are in a series configuration is the following equation. And if you have capacitors arranged in both in a series and parallel configuration, what you would do is find the capacitance of all capacitors in parallel first, then add up your final parallel capacitance or capacitances. You would just find the total parallel capacitance for each group. And once you've done that, you add the total parallel capacitance with your series capacitance. And C parallel can act as C1, C2, or C3, and so on. So your total capacitance and the equation for it and the equation to find it could look like this. And just keep in mind, find C parallel first, then add it up with C series. And I will go ahead and make an example circuit diagram showing how all of this works. And here is my diagram here. Another thing that I would like to mention is that your components that come after your first intersection point and before your last intersection point are going to be components that is most likely going to be in a parallel configuration. And you can check whether that's true by taking a look at the polarity of those components. So if a negative lead connects to a positive lead, those components are going to be connected in series. But if a component's positive side with the positive side of another component, then you have those two components in parallel. And if you have the component of the negative side connected to the negative side of another component, that also indicates that those two components are in a parallel configuration. So as you can see here, I have my two positive leads connected together, that's in parallel, and my two negative leads that are connected. And here's my positive lead, here's my negative. My negative lead connects to my positive lead here, making it a series connection. Positive, negative. And to find our total capacitance, let's go ahead and find the parallel capacitance first. We know that these two components are in parallel. To find the total parallel capacitance, we just simply add 300 farads by another 300 farads. Then we can add the parallel capacitance with our series capacitors that has the capacitance in series to get the total capacitance. So we can write down the following, and for the total capacitance, we get 60 farads. And also keep in mind, whether your capacitors are in parallel or in series, no DC current is going to go through them unless an alternate path exists. And if you want the capacitors to discharge and allow the DC current through to complete the circuit, all you have to do is add another component that has a resistance or impedance value. Just to make an example by making another schematic diagram, here I have a capacitor in parallel with an LED. And this LED would allow the DC current to flow through it, completing the circuit. But just keep in mind that the capacitor here still acts as an open circuit when it's fully charged. So let's go ahead and add a switch to this circuit now. So here I have my new circuit schematic, and here is my switch. This is the symbol for a switch. In the open or off position, when this capacitor here is fully charged, what happens is that when the switch is turned off, the capacitor would discharge its electric energy from the positive side to the negative side. And this is possible because a path exists that connects these two terminals together. So it goes from here, goes through the LED, and goes through the negative side. And this capacitor would continue to supply the electric energy until it's fully discharged. So the new path would go here, and the previous path, going back to this diagram, would go this way continuously, and it would go this way up until this capacitor is fully charged. And if I go back to my previous notes here, one of the requirements that the electric energy could be discharged from a capacitor is that if a path exists that connects the capacitor's positive and negative terminals together, and if the capacitor isn't charging. So here I have my LED in parallel with my capacitor for this circuit board here. And for this circuit board here, I have my capacitor in series with my LED. And I will show you the difference between these two configurations. So here for my series board, what I did for my left side is that I connected my resistor first, then my capacitor, then my LED. And this red switch here serves to connect my positive lead and my negative lead of my capacitor together. And for my right side, I attached the capacitor first, then the resistor, then the LED. And the red switch here serves the same purpose. So right now I have both switches off, meaning the leads aren't connected together. But if I turn this switch on, you can see as the capacitor is charging, the negative charges are being pushed out, lighting the LED for a short time until the capacitor is fully charged. And the same effect happens on the left side too. So moving my gray switch to the left side, if I slightly tap the red switch, so if I turn it fully on, the LED is fully on, turn it off, and you can see the LED discharging. However, if we put our capacitor in parallel with our LED, we would get a different result. So here the LED is always going to flash on because the DC current would go through the LED. But once I create an open circuit by cutting off either the positive or the negative lead, the capacitor would be the one that supplies the electrical energy to my LED. And as I release my negative lead, you can see that the LED slowly disappears. And if I connect it back, the capacitor is charged, DC current goes through the LED. The last thing that I want to talk about is what RC circuits are used for. And two examples that I can think of from the top of my mind is low pass and high pass filters, which is relevant for sine waves or for AC signals. And a high pass and low pass filter will determine which frequencies are allowed to go to its output and which ones would get damped out. If you recall from our impedance equation, we have our capacitance impedance is measured in ohms, so we can replace Z sub C as the following. And finally, to find our frequency, we get this final equation. And as you can see here, the frequency is dependent on the values that you used for the resistor and the capacitor. And this frequency acts as a cutoff. It would define which frequencies of your sine wave or your AC signal would be normally outputted and which frequencies would be attenuated or damped. And I will go ahead and write down the conditions for a high pass and low pass filter. So essentially for your high pass filter, it would allow high frequency signals to go through, but if it's low frequency signals, it would be less noticeable. And for your low pass filter, lower frequencies would go through, but higher frequencies, but in reverse, the higher frequencies would be less noticeable. Would define which frequencies are going to be high frequencies and which frequencies are going to be low frequencies. And the construction of your high pass and low pass filter would look like this. So here I have my symbol for capacitor, I have my symbol for a resistor, and I have my symbol for ground. Your input sine wave or your AC signal would come from here, and your output or your resulting sine wave or AC signal would come out here. And same goes for the low pass filter, except instead of your capacitor being your first component, it is going to be your resistor. And I'm going to go ahead and make a high pass and low pass filter, and I will use an oscilloscope to show my results. So here I've made my low pass and high pass filter. My right side represents my low pass filter since my resistor component is first, and my left side represents my high pass filter since my capacitor is my first component. My red wire represents my input signal, my black wire represents ground, and my blue wire represents the output signal that I will see in my oscilloscope. So here I have miniature clamps that connect to my oscilloscope's wave generator, and I will be testing the right side or my low pass filter first. And I have my oscilloscope probe where I will observe my result, and this would go to my output of my filter. And you can see that I've attached everything like so. For the components that I've selected for my high pass and low pass filter, both my capacitors have a 1 microfarad capacitance, and both my resistors are rated at 1000 ohms or 1 kilo ohms. And if we want to find the cutoff frequency of our low pass and high pass filter, we would just use the frequency equation that we've discussed before. And substituting my R and C values in, I would get a cutoff frequency of 159.15 Hertz. And remember, low pass filters allow lower frequencies to go through, and high pass filters allow higher frequencies to go through. So here, my oscilloscope has a built-in wave generator, and the option for my wave generator is right here. Now for most oscilloscopes, you might not have an option to generate a sine wave or your own AC signal. And for this case, you will either need a signal generator, or for a sine wave, you can use a variac, which I have one right here. You can use either of the three options. Any one of them is fine to test your high pass or low pass filter. But for this demonstration, I'm going to go ahead and use my wave generator on my oscilloscope. And here I've turned on my wave generator for my oscilloscope, and below my screen of my oscilloscope are the options that I can pick from on my wave generator. So right now my wave generator is outputting a sine wave with a frequency of 61 Hertz, an amplitude of 6 volts peak to peak, and no offset on my waveform. So here, if I wanted to change my frequency on my oscilloscope, I just simply tap the frequency option, and I can adjust either increasing my frequency or decreasing my frequency. The yellow sine wave that you see on my oscilloscope screen represents the output of my low pass filter. And as the frequency cutoff is 159 Hertz, as I adjust my frequency above 159 Hertz, you can see as I increase the frequency further, my amplitude or voltage peak to peak is decreasing. And this is what I mean when the signal is being attenuated or being damped. And as I further increase it, you can see my peak to peak voltage is decreasing here. And if I decrease my frequency, my voltage peak to peak will be much closer to my 6 volts that I have defined for my amplitude. So if I decrease my hertz, you can see my peak to peak increasing. And yeah, it goes to 6 volts or even a little bit above. Anything below 159 hertz would have its normal amplitude. And going back to my low pass filter that I'm using, this red wire and black wire is connected to my wave generator, and my blue wire and my black wire is connected to my oscilloscope probe and ground. And if I switch my attachments from my right side to my left side, which is now my high pass filter, my attachments would look like this. And going back to my oscilloscope screen, you can see that for a high pass filter, because my frequency is way below 159 hertz, my peak to peak voltage is significantly reduced, and it's even close to 0. But as I increase my frequency, I tap this option and increase it further, you can see my peak to peak voltage increasing, and that should go up until whatever my defined amplitude is for my wave generator. And I've noticed that my high pass filter has some imperfections, which I encourage you to check with your oscilloscope. But yeah, this is pretty much the gist of your high pass and low pass filters. That'll be it for this video. I hope you found this video helpful. Thank you.